Morning student, this is continuation for previous video. The topic is data representation. So before that, there are 7 types of data representations in computers. First one is data type, second one is complement, third one is fixed point numbers, fourth one is floating point numbers, then sixth one is other binary codes, last one is error detection codes. Now this is the third one for data representations. The topic is fixed point numbers. So before going to discuss any digital computers use binary number system to represent all types of information inside the computer. I already told you there are 4 different data types for supporting any digital computers. That means the most commonly used digital computers for binary numbers, that is 0 or 1, then octal numbers, decimal numbers, hexadecimal numbers. These are the data types for supporting any digital computers. But in our question is how to store real numbers, in a computer. So in a modern computing, there are 2 major approaches to store real numbers. One is fixed point numbers, another one is floating point numbers. So real numbers means a number with a fractional component. You know that it's a real number and a number with fractional components. There are two approaches for storing real numbers in digital computers. One is fixed point number, that is fixed point notation. Another one is floating point notation. Now we are going to see fixed point numbers only in this video. First, binary fixed point representation. A binary fixed point representation, there are 3 parts. One is sign field, another one is integer field, third one is fractional field. See that uh, there are 3 parts. One is sign field, that is x equal to xn minus 1, xn minus 2. This is the sign field. Then another one is integer field, x1 x0 is a integer field, dot x1 minus 1 x minus 2. So this is the fractional field. So totally 3 fields. It represents a fixed point numbers. Basically a sign bit represent 2 numbers. One is 0, another one is 1. So 0 means it is a positive sign in binary. 1 means it is a negative sign. So you remember that in digital, sign bit, that is 0 for positive, minus 1 for negative. All the remaining bits are called magnitude forms. All the remaining bits, the first bit is nothing but a sign bit, then all the other bits are called magnitude bits. So there are 3 representations under this condition. One is sign magnitude representation, second one is signed ones complement representation, signed twos complement representation. So these are all the 3 representations under the fixed point notation. So here one example is there, plus 9 and minus 9 in 7-bit binary number. So 9 will be represented as 7-bit binary form. So 9 is nothing but in binary form 1001. 1001 is a 9, but it represents 7-bit binary form. So you can add 3 0. So first bit, that is 0, in most significant bit, first for 0 is a sign bit. All other remaining 6 bits are called magnitude bits. So in the 9 is a plus sign because the 0 is represented as a positive. The most significant bit becomes 1, the number is called a negative sign. So the minus 9, there are 3 ways to represent the minus 9. So there are 3 ways. One is signed magnitude, signed minus 1 complement, signed 1's complement, signed 2's complement. First, in signed magnitude method, The 9 is represented as 001001, but in the first most significant bit is become 1. So 1 means that is the sign bit only complemented. That is a sign bit before in plus 9 the sign bit is 0, but after I am complementing the bit sign bit becomes 1, all other remaining magnitude bits are same. So this is sign magnitude, only it change sign bits. Then second category, signed ones complement. Here sign bit and magnitude bits are changed, that is complement for all the bits, sign bit including magnitude bits. So sign bit is 0, that is complement of 0 is 1. The next 0, the next bit is 0, so that's also complement. Then next 0 will be complemented. Then 1 is 0, it changed 1, one's complement is 0, then 0 0 for 1 1, then last bit for 1 it is complemented for 0. So all the bits are complemented for one's complement. The next is 2's complement. For applying 2's complement, here sign bit is sign and magnitude bits are both for changing the complements, as well as you can add one for least significant bit, that is LSB. Before that, in sign 1's complement, the result of sign 1's complement is 11101110, but in 2's complement, the 1's complement number, then add 1 for least significant bit, that will change 2's complement. Simply can try this. So this is for fixed point numbers. We go to next for detailed explanation for some other characteristics. Characteristics of three different representations. One is sign magnitude, another one is sign 1's complement, then sign 2's complement. So here clearly pointed out, sign magnitude complement only the sign bit. Before I am telling you, only the sign bit will be complemented. Sign 1's complement of all the bits including the sign bit. Then third is 2's complement. Take 2's complement of the number including its sign bit. 2's complement means first you find 1's complement. After that you can add least significant bit for 1. That becomes a 2's complement of that number. So this is the characteristics of three different representations. We go to next. So this is arithmetic addition. That is signed magnitude, first method. So there are four rules are there. First one is compare their signs. Compare their signs. Compare their signs means both or two numbers becomes positive or negative. Check the numbers are positive or negative. These two signs. If two signs are same, second step. If two signs are the same, add the two magnitudes. Add the two magnitudes. Look out for an overflow. In third step, if not the same, that is two signs are not same, compare the relative magnitudes of the number and then subtract the smaller from the larger. So needed a subtract to add. So suppose if the signs are not same, on that time you can subtract the smaller from the larger, that is smaller to larger. So larger number is top, then smaller number is bottom. So you can subtract it, get the result. The last point, determine the sign of the result. So for the last one is you find the sign of the result. After adding or after subtracting, you can find the sign of the results. Here there are some examples. First one is 6 plus 9. So you get it, you got it, 6 plus 9 is both the number, the signs are same. So 6 is positive, then 9 is becomes positive. So you can directly add 6 plus 9 is 15 generally, but in 6 is converted to binary form is 0 1 1 0. The 9 also converted for binary 1001. So you can add 0 plus 1 for 1, 1 plus 0 for 1, 1 plus 0 for 1, 0 plus 1 for 1. So 1 1 1 1 is nothing but 15 in binary form. So simply we can add for both signs are same. This is very simple. In second example, minus 6 plus 9, here the signs are different, so you can interchange the magnitudes, that is larger to smaller, that is subtract smaller from the larger. So smaller number is 6, then larger number is 9. So you can change 9 is for binary 1001, 6 for 01, 10. So you can subtract it. 1 minus 0 is 1, 0 minus 1 is 1, then borrow is 1. So 1 minus 1, 0. Then 1 minus you can borrow it for adding. So 0 minus 0 is 0. So finally we get the answer 0, 0, 0, 1, 1. So 1, 1 is 3. See, this is subtraction. Suppose if both numbers are minus, but the minus 6 plus minus 9, the last one, minus 6 plus minus 9, directly you can add it, that is 6 plus 9 is 15, the sign is minus. So this is the logic for arithmetic addition in sign magnitude form. There are four ways. One is compare their signs. If the signs are same, directly you can add it. If the different signs are represented, the compare is relative magnitude, that is to subtract the smaller from the larger, that is different signs means. Okay, go to next. Arithmetic addition for sine 2's complement. Before that, arithmetic addition for sine's complement. Here sines signed 2's complement. Here add the two numbers including their sign bit and discard any carry out of leftmost bit. Here you can add the two numbers, any two numbers, that is 6 plus 9. I am taking only two numbers, 6 plus 9. So add two numbers including their sign bits and discard if have produced any carry for leftmost bit. So suppose we can add 6 plus 9, that is 6 plus 9 for it representing 0 1 1 0 1 0 0 1. Here the sign bit is 0 0 because of it is positive, so you can add sign bit for 0 0. So you can add it. 0 plus 1 1, 1 plus 0, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0. So you can discard it leftmost sign bit. So the result is 1 1 1 is 15. Here one example for minus 9 plus minus 9. Here we get the sign bit. You can remove it for the sign bit. So 9 minus 9 plus minus 9 is minus 18. So I can the minus 9 directly it changed sign it changed in binary form, that is 0 1 1 1 is not a 9. Before that plus 9 is plus 9, our plus 9 is 0 1 0 0 1 is a plus 9. It is changed in negative form, that is negatively. That negative means for complementing both sign and magnitude numbers. So 0 complement 1, then 1 complement 0, the next 1 1 1 for, that is 0 complementing 1, and the last bit is 1, so it is complemented as 0. So then it changes 2's complement for 2's complement. So that's why first you find the 1's complement of minus 9, then you can add least significant bit bar 1, so you get the answer 1 0 1 1 1. So both minus 9 means you can copy the same number 1 0 1 1 1. Now you can add the number 1 plus 1 0, 1 plus 1, that is 1 plus 1 0, then carry 1. So you can add 3 1, you get 1 1. So 1, then again carry 1. So again add 3 ones, 1 1 1 for 1, then carry 1. So 1 plus 0 1. Last finally 1 plus 1 is 1 0. Now you get the leftmost carry. You can remove is, that is discard for if produce any carry of leftmost bit, you discard it. So finally you only for adding, only forget the resulting bit. Okay, so this is the arithmetic addition of signed 2's complement. We go to next. Arithmetic addition of signed 1's complement. So this is very simple, only one rule. Add two numbers including their sign bits if there is carry out of the most significant bit. If any carry out of the most significant bit, the result is incremented by 1 and the carry is discarded. So this is totally different from 2's complement. Whereas in 2's complement you can remove the leftmost carry. Here you can add the most significant bit. If you produce any carry out of the most significant sign bit, the result is incremented by 1 and the carry is discarded. So here I am taking one example, that is 6, then minus 9. So minus 9 already, the result is the minus 9 for representing 1 0 1 1 0. This is minus 9 of 1's complement number. But 6 is directly uh, directly to take sign number and magnitude bits, that is 0 is sign number, 0 1 1 0 is a magnitude bits. So now we can add it, 0 plus 0 0, 1 plus 0 0, then carry 1, so triple 1 for 1, again carry 1, so then 1. So here does not produce any carry, so you leave it. So again minus 6 plus 9, end around carry. Here you get the end around carry, minus 6 plus minus 6 for representing to complement sign number, to complement both sign as well as magnitude number. So the 6 will be complemented 1 1 0 0 1. You get before in plus 6 0 0 1 1 0, but in minus 6 it complemented for both sign and magnitude form, so it changes 1 1 0 0 1. Then plus 9 is 0 1 1 0 1, so you can add it, 1 plus 1 0, carry 1, so 1 plus 0 1, 0 plus 0 0, 1 plus 1 0, then carry 1. So carry bit, again you can add the sign bit also. So 1 plus 1 0, then carry 1, you can get the end around carry, that is the most significant bit carry. So you can add the resulting bit, that is the resulting bit is 0 0 1 0. You can add the 1 for resulting bit, you get the answer 0 0 1 1. So 1 0 0 1 1 is 3, so 9 minus 6 you get 3. So this is called arithmetic addition for signed ones complement. Okay, next.